So I'm going to show you one of the use cases of what's very popular use case of Spark, which is a recommender system. And I'm gonna show you this inside a scenario of a hackathon that really happened last year. So I'm going to talk to you, before I moved to Milan to work in Pirelli, I was part of the Barclays data science team, and we were working in London and in the retail business banking department. So back in time we were around 6 members, a mix of engineering and machine learning specialists, and at a certain point we had to kick off a new project. That was a recommender for so this business wanted us to build a model for recommending shops, like businesses or customers. So if you've never been in a particular shop around the corner, then if we can see from your shopping behavior that you might be interested in that shop in the corner, then we like to build a recommender. So we had to start a new project from scratch, and then we say, why don't we, all go together? We're at the villa, and we go to an exotic place like Lanzarote. We went there in December for a week, and we say for 5 days we're gonna go from there and we're gonna build this recommender. So the major technical challenges that we faced, first of all, we have been in the Canary Islands. You know that internet is so slow. So the best connection you can get is 1 gig, and that was through a router like this one. So we had to build, test, and refactor our solution from scratch, and at the same time we wanted to run an end-to-end evaluation, but we didn't spend like hours for our evaluation because otherwise we wouldn't be able to finish it by the end of the week. So, and the other challenge was we would like to all work with common data structures, with a common API. So if you're familiar with Kaggle, we kind of want to do the same thing, like you plug your solutions at a framework, and then the framework will automatically tell you how good is your solution. Pretty much like Kaggle. And at the same time, we also wanted to build something that is not just a toy model, it's not just a proof of concept, but when we went back to London, that was actually production ready. So that was actually the cool challenge. Is imagine in morning, on one hand you need to code, and otherwise your boss is going to be very upset because you don't do it. But at the same time you're on the island, so you have to wake up early in the morning, go surfing, and then you come back and you need to code till night. Otherwise you won't be able to learn. Right. So one of the Bible that we try to follow as a guideline. Sort of best practices guideline to follow and what we built was the professional data science manifesto. So I already mentioned this in the first event. It's a kind of initiative similar to the Agile Manifesto. It was born in 2001 after the dot-com bubble. Dot-com bubble, what happened was everyone was doing programming. Everyone started programming websites, applications. Everything was so messy and dirty. And then the industry realized that, now we need software engineering, because otherwise it's not going to work. So they came out with this idea of the Agile Manifesto. Today, we are in a kind of similar situation with data science, where everyone is doing data science, no one really knows how to do it. There are low ways to do it. In a more enterprise-ready way of doing data science, then there was no any sort of best practices or guidelines. So we followed this manifesto, which I'm not going to show you details, but we're going to see at the end of the slides how we agree with the principles. And technology-wise, why did we choose to use Spark? Just name a few. So in the previous talk, I already mentioned a few reasons. So our particular use case was, first of all, speed and performance. We wanted to do an elastic job. Elastic job means you write the same code that works locally in your machine and then magically scales. So no matter what is the infrastructure behind, it's the same code, and independently of the data size, it just automatically scales. No need to do any further action to make it work. And also Spark is a very complete framework. It's not just a replacement of MapReduce, it's actually a platform. It's a platform where you have everything, from the reading data from a data warehouse to processing in your ETL, doing machine learning and plotting and putting that deploying to an API. So you can do everything in a single platform. That was very important. And because it's built around functional programming API, it's very, very productive. So it cuts development time, and you don't need to worry about debugging your code. As long as you follow the right functional principles, then you won't have bugs in the code always. That's never true, but you're going to reduce a lot the number of bugs in the code. Right. So just before so obviously it wasn't reasonable to do the ETL while we were there. First of all, there was no connectivity, so we couldn't connect to the production cluster and get the data. So we had to do a little bit of preparation. So we did the ETL, clean, extract some data, clean some data, blah blah blah. But the very important thing was that in order to export the data, we had to anonymize it. So the data I'm talking about are transactions, like credit card, debit card transactions. So we selected a single town of Bristol, and we extracted the whole transactions of everyone living in Bristol, and then we anonymized them. The anonymization happened using K and anything that, if you're not familiar with, is an algorithm that essentially what it does, it groups, it reduces the resolution of your data by grouping, let's suppose there is a cluster of users, similar, then you don't represent the feature of each single user, but you represent each, sorry. Works. Okay, thank you. So when the way it works, you create an object, you serialize it. In that case, it's generally convenient to use hash maps. So you take the small data set, you create a hash map dictionary that shuffle and broadcast to each single node. And then locally, each the distribution of the big data gonna be partitioned, right? In each node, and each partition is gonna do the join locally just by looking at a hash map. Okay, so after we have defined the data type, the APIs, now first thing we built was the evaluation framework. So this is very good advice. Before you start implementing a model, a solution, whatever, try to first focus how you're going to evaluate how good is your solution. Do implementation next. At this stage, what we did was we're going to evaluate that way. We're going to take all the data. We're not going to shuffle it randomly, like, 80%, 20%. No, because then you're going to create data leakage. So we need to group the same transaction of the same user all together. And then for each user, you decide which fraction of the business is going to be in the training and which fraction will be in the test. And then all the transactions belong into the same combination of user and business. They either go all of them in the training or all of them in the test. You never mix it. And then that's the way it works. See? So I specify you, please evaluate this recommended training. This is training data, this is test data. So what it does is, alright, I call train on your trainer with the training data. Then you give it back the recommender model, and then I'm going to ask the recommendation for the test customer. Very easy. We did a bunch of checks here to make sure that you're not cheating. Because if I ask you, I'm going to give you a list of 10 customers, then I expect you to give me a recommendation for exactly those 10, and exactly n recommendations. I don't want to see other users, less users, more recommendation, less recommendation. Exactly what I asked before. And then ultimately we compute the mean average precision. What the mean average precision is this comes from information theory. Suppose you have it's generally applied to documents, but you can apply to recommenders. So let's suppose that you have each customer has visited m relevant businesses, which he thinks, oh, those ones are actually interesting. And then you recommend n, okay, give me n. And then from 1 to n, you start calculating the precision at different cutoff points. So the first cutoff means give me only the one recommendation, and then you check what is the precision. And then ask, okay, now give me top 2, and then you compute what the precision with the top 2. Then you ask, oh, give me top 3, top 4, top 5. And then each single time you compute the precision at each cutoff point. This is an example. Right, you got Bob on top, and Bob likes the, you can give him as a brand. There's no name, just brands. And then this is the output of the recommendations. That particular model says that Bob is interested in this, and this. Where the yellow box means something not relevant. Fine. Now, first cutoff point, if I only ask you for 1, you have 100% precision. If I ask you for 3, you got 2 out of 3. If I ask you for 6 recommendations, you only got it right 3 out of 6. So you sum up all of those, and the reason why we sum up different cutoff points instead of just taking the last one is that it's very important order of where you put your recommendations. It's not just about giving top n, but also care about how you rank them. Ultimately, what you do the same, you repeat the same for each single user, you do the same with Alice, and then the average. Fine. Now, we need to create a baseline. A baseline is something you can do quickly. This should take 10 minutes, no more. So, this is the code for creating a recommender of the most popular businesses. The way it works is during the training, all you have to do is to kind of reduce or count how many distinct number of users each business has. Then you store it. It's a static list. If you know that I'm going to ask you for n recommendation, you need to store the top 2 times n. And the reason for that is that you cannot recommend something that the user has already visited. You need to recommend something new. So let's suppose that in the worst case, the user has visited already the top of the most popular n, you need to recommend the next n. So if you have 2n, then you can do it. And you simply, what you have to do is to take this rank businesses by number of customers, which is in the form of a broadcast variable. For the same reason as I told you before, is that take this object, and in this object will be available in each partition of my customers. So if I get a broadcast variable, then I can do the join map sum join. And take the top n. That's it. Now we're going to go into things that are more interesting. First family of recommenders is customer-to-customer similarity models. In very few words, you take one customer and you project it into a feature space. And then you define a metric space so that if you have 2 users, 2 customers, then you can compute the distance. Or the similarity, which is 1 minus the distance. Now, particular case. So the feature space depends on 2 things. Common behavior, and common behavior means shopping patterns, like where you shop and when. Demographic attributes is like age, job, gender, those kind of things. This is a representation of the case class that represent features for each user. It's a bunch of maps. Each map corresponds to one histogram. And the histogram is a distribution. It could be seen as a probability density function, where in the case of, you can see as a normal distribution where you have day of the week, you have 7 days, Monday to Sunday, and then you have the percentage of spending over the week. And then likely you do the same. You can see the postcode sector in the city. Because I shop mainly in that area of the city. I shop in the north, I shop in the south, I shop in the east. Category is the merchant category. So I'm interested on buying sports, clothes, and you're interested in a restaurant. So this is your distribution of how much you spend in a restaurant and how much you spend in sports clothes. Then you can do this for any shopping part, any shopping dimension you have in your data. You can build a distribution. Then the last ones with the attributes. This comes from the bucket during the anonymization, because what's the point? Say, oh, you have a PDF for your gender. Like, I'm 30% male and 30% female. That doesn't work. But because you don't know whether the user is male or female, because it's been anonymized, that's why you have this distribution. So if you take those all those maps and we flatten them, then we get a long vector. And the long vector, you can compute cosine similarity with all the users. That's the way you do that in Spark and Scala. So you take, so this utility function which takes the data, and then it maps this one, you map the customer ID and the second dimension which you want to aggregate, which you specify. And the second dimension could be the day of the week, the category, the postcode sector. So whatever you want to aggregate, this is the second column of your join key. And then you create a tuple with the key and one. And then you do reduce by key. Reduce by key means for every single record of the same key, I'm going to apply this operator. And the operator is the sum, because this is a number. So this is a monoidal way of doing aggregations. It's a more scalable way to do aggregation in a distributed fashion. That is very simple. The reason why you don't do group by directly, you could, is because you can do group by means you group all the records of the same key, and then you count how many records you have. This is exactly the same thing that you do here, but you don't really need to shuffle the whole records, because all you care is about the count of records, not the record themselves. So you remember this: group by is not for aggregations. That's a misconception that came from SQL. Group by means group by. So the word itself in English means taking all the stuff and grouping them. So when you talk about aggregations, you're not grouping, you're doing something different. So reduce sounds more like aggregation. After the reduce, we have a group by, and here you can do that, because what we want to do that is a really grouping by. So it's different, we're not aggregating here. Say so. This is just because we want to extract part of the information that we did during the reduce. And then we build this map, and then we normalize, essentially take the sum and we make it so that it's set to 1. The only exception was for the businesses, because the businesses we had to cut. We couldn't do a long histogram with a single business because it would be too much to remember. So we had to take just the top 100 or so. Anyway, so too much details here. Probably gonna skip because it's too much. Just one thing. Remember, when you create broadcast variables, they exist forever until you stop your context. So if you create a broadcast variable to a join and then you don't need the broadcast variable anymore, then remember, you need to destroy them. Right, so now that we have a representation in a feature space which for all the users, now we can do k-neighbors. All of you are familiar with k-neighbors. If you're not, is a very simple algorithm. You start with one point and you define a radius, and then simply, oh, give me, you ask, give me all the points within this radius. We did this in a very efficient way using a data structure called BP3, which I'm going to show you in the next slide. So let's suppose you have a magic data structure that whatever you ask in a very quick time gives you the answer. And once you find all your neighbors, you look at all the businesses that your neighbors have visited, and then you assign a weight which is proportional to the similarity score you got with this user, and so on. So that's it. DBP3, which is vantage point 3, it's a tree data structure where it's very good. It's heuristic, first of all, and it's very good for fast spatial search. So take all the points, and then in analog and apply, you build the data structure. After you build it, you can say, okay, now I give you the entry point, I give you a radius, give me all the neighbors. And this happens in logarithmic time. It's very good, check it out. Now, the second family of recommenders is business-to-business models. That means we need to, instead of creating a similarity matrix between each pair of users, now we create a similarity matrix based on each pair of businesses. So we got the matrix here. I know there's a mistake because I think this one was supposed to be swapped with this one. So let's suppose that this one are swapped. Then what those numbers represent is the distinct number of users they have in common. So my shop, your shop, we have in common 10 users, and so on. So that's the way we build matrix, and now we can compute the similarity between each pair in two ways. The most standard one is the conditional probability, but a little bit better way is the tiny model coefficient. So I'm not going to tell you what the tiny model coefficient is, even I don't remember, but check it out. It works better than conditional probability. So that's an example of the way the algorithm works. So you have your entry point, which is, say, Bob. And Bob has shopped previously in A and E. Then A is linked with all the other businesses through a similarity score, which is proportional to the affinity of the two businesses in terms of number of common customers. So once you build that, you need to do only one normalization, because you cannot recommend a business that he has already visited. So we set all of the connection to the business of the first level. Here we set them to 0. So we make this one unreachable. We make this one to not be able to reach this one. And then all the weights that we lose here, we need to redistribute to the other business so that it sums up 1. It's a very high weight. There's no any math behind, so it's just good. This is not science. This is more hacky recommenders, like many things in machine learning. They just work. This was just a proof of concept. This was a hackathon, so don't focus too much on those details. It was more, we need to get it done by the end of the week, kind of things. Then you propagate the weights left to right. You can apply a sort of a probability rule here in order to compute the final score for each business. And then you rank them. So the first one is going to be C, the most recommended one, and then the second one is going to be D, and then D. had a hybrid approach. Not gonna find this one over. We just was a matter of creativity. Say, what if, because we found the two models to be kind of comparable. Say, we need to join the forces. We need to make it so that we use both the information of the customer similarities together with business similarity. And we build neighbor to business. The way it works is we add an extra layer by piping together the two graphs. So you start with one user, you get the K neighbors of the customer. The neighbors of the customer has businesses, and then the businesses of your neighbors also have neighbors. Very good. So you got Bob, and Bob got two direct connection to those, A and B. But Bob also is very similar to aliens and people. So aliens and people, they have a connection to those shops. And those shops is a full mesh with all the shops in the dataset. So we add an extra layer here. And by doing a similar thing by normalizing and reaching the level, you can get a propagation left to right, the weights. And what you get at the end is a score which takes into account multiple things. And you even extend your radius, because even though if you only look at K neighbors and there's a new shop that no one has ever visited, then you're not going to find it, because neither your neighbors, they have a shop there. But by doing this and this, then you have a chance to find it. I'm not going to show you, I'm not going to explain it too much here. It's a copyright, no, I'm joking. This is actually open source. We just want to say that whenever you look at this level of connection, if these two have a direct connection with the Bob, you're going to skip all the connection between the neighbors and this, because you already know what is the affinity score with this one. You don't go through an indirect path. Right, so then we move into more matrix factorization models. This is mainly, you take a matrix of the transactions where you have user, businesses, and then you decompose it into a customer to topic and topic to business. This is called latent semantic analysis. So take the whole matrix. The algorithm, the model will automatically find out topics, and then you're going to represent users in terms of topics. Like I'm 55% interested in sport, and I'm 30% interested in traveling. So by representing users and with these topics, then if I like sport, then I'm going to recommend you all the businesses of sports. And if there's a topic which you're not interested, then I'm not going to recommend you any of the shops that are not this topic. ALS is available in Spark and MLlib, but you will find out that there's a little bit of extra work that you need to do in order to make Spark and MLlib work for the particular machine learning models. So I'm first going to show you how to use ALS. There is a case class from the Spark framework here, which is the 18. So you need to create a table. You got the customer ID, which is a number. You need to specify the business ID, which is the I and J. So you got the row index and the column index of the original matrix. And then the number here is your rating. Now our use case, previously we only counted once. So if the user has shopped once or has shopped 1,000 times in the same business, it doesn't make any difference. because we compute everything in terms of this number of users, this number of businesses, and so on. In that particular case, we actually need to put a rating here, pretty much like you do with mortgages. The rating is the count of how many times, how many transactions the user spent in this business. In order to do so, remember, our representation of the business, remember, was merchant town, merchant name. So we've got two strings, and now we need to turn two strings into number. Again, how we do that? This is the amazing thing about Spark. Very simple, one line of code, take your data, map into business key. So now we've got a collection of business keys. Take the distinct set of those. Then zip with unique ID means you're going to create a tuple with the original value and a number which is unique for each key. This is already part of Spark. It works really this stupid way. And then you mark the values, you take just the right one, it's a long, because if your collection, the number of elements in your collection doesn't fit into an integer, then you have overflow problems. So generally, Spark returns long. So we turn the long into an integer, then collect. Collecting, if you remember, previous node means when you run Spark job, you have a driver, which is your master node, and then you have the executors. So when you collect, you're essentially moving from a distributed environment into a local environment. So you're taking all the results, which now you assume to be small enough to be fit in memory, then you load it. After you load it, you turn it into an hash map, and you broadcast it. So this broadcast variable is a broadcast type map, where you got the business key, and you got the unique identifier. So take this one, and then you inline in here. So now you can replace each business key with a number. You again, see what I do? I create a tuple where the right element is 1, and then I do reduce by key. So this is again a way of doing the counter transactions in your data in a monolithic fashion. And then I create the ratings object. Now, the problem with ALS is that you do the training that way. And then the training, what it does, essentially creates a decomposition of user and business representation. The problem is that when you try to do a recommendation with these objects, then it's going to trigger a distributed job. So even though the user is small, because when I ask you for a recommendation, I don't give you millions of users, I give you like 1,000. Let's say, when I do the evaluation, I only ask, I'll give you a recommendation for 1,000 of those. And it's not really convenient to do the linear algebra in a distributed fashion if your matrices are small, especially if you're doing that in a laptop. So we had to implement the linear algebra ourselves here, but not gonna cover too much. The only thing we did was just a very high overview. Take a customer, and you previously have computed all of the businesses that he has already visited, unless it's a new user. So if it is a new user, this one. If it is a new user, then give me the most popular ones. If it is a user that I've already seen, then take all the list of businesses that I can recommend you, remove the one that he has already visited, get the user to topic vector representation that you learned during the training. After you got the user vector, then you take all the businesses that are recommendable, that are eligible to be recommended, you turn them into a matrix of top business. Actually, it's double matrix, but it's actually a vector. Take this vector and then do the dot product. So we had to do this ourselves through broadcast variables. Otherwise, the Spark implementation wouldn't work fine for big data sets, but for small data sets, that was our implementation that worked better for us. So now let's suppose that you got a long list of businesses. And now we need to take the top 10. Typical way, a simple way to do that is, okay, I sort the whole list, and then I take the first n elements. This is very expensive. First of all, if you need to sort, it's n log n in the best case. And then you need to keep all of these in memory. So we created a kind of, in a purely functional way, we created a folder, an accumulator, where you take all the elements in no matter which order, and you fold them into a buffer. This is the notation in Scala to do fold left. Take the elements, so at the beginning the buffer is empty, the accumulator is empty. So the first n elements, they go to the accumulator straight. And then you get a new one, and then you check whether the smallest in the buffer is actually bigger or smaller than the other one track. So that you know beforehand, oh, this one is smaller than the minimum n, cannot be in the top 10 at the end. And that way, you only have to keep in memory the k elements that you, n elements that you want to return, not the whole collection. Then we try also other approaches. We try building a covariance matrix, which you represent users, pair of users, in terms of how much. So if they have co-occurrences of patterns where they shop, then you can build a covariance matrix, and you can then make recommendations based on that. And we even try to build a random forest, which like thousands, hundreds of thousands of random forests, where for each single business you build a pattern classifier. And so when you have a new user, you need to recommend, you can run the user through each model, where each model corresponds to one business. And the binary classifier is going to give you a score which says this is a number. It was a showcase of a little bit of different approaches. Now I'm going to show you the winner. So the baseline was just 3% of precision, and keep into account that precision in a recommender is not the same as precision in a binary classifier. In a recommender, precision is very low, because imagine like when you have an advertisement, then do you have a click? Like your click rate is so low. So actually converting a person with a recommendation is generally very low. That if you can achieve even 2-3% is already a lot. Because think that way, you have big chains where almost everyone goes and shops. So if I'm in the UK and I recommend you, oh, you know what? I think you should go to Tesco. Then, of course, everyone in your life, you've been Tesco if you have lived in the UK. But if there is a very niche corner shop, very small targeted user, they're doing a single thing, very niche, then you're not interested. So the prior is very low. Why do you care about shops on the street? You don't care generally. So if you can achieve these numbers, it's already a lot, very cheap. The winner model was the neighbor to business. By 16%, that was a huge gap in the second. So that means that if you are focusing more on solving a problem rather than implementing a particular model, you'll find out that you can do a lot of stuff just with counts and divisions. You can achieve a lot. Now, a few limitations. The framework, as I say, ML and ML-lib, they have purely private fields. That means you train a model, and then everything in the model is private, so you can't access it. And you can access a few things, but you cannot access a few functions. So, for instance, if you're doing binary classifications, then the binary classifier model of ML-lib, it tells you whether it's 0 or 1.
But if you want to get a score, it's not going to tell you. So you need to, based on what the model is, you need to recompute the score. So if it's a decision tree, you can only access the top node of the tree, and then you need to traverse the node, the tree, and recompute the score yourself. That's so crazy. And also, majority of machine learning algorithms are implemented in linear algebra, which they have very well optimized for that particular algorithm model. The problem with them is that if you want to do your own linear algebra, because you play with the map, then it's not really clear how to do that. So at the end, we had to bring external libraries for doing linear algebra in a distributed way. Because the linear algebra, the generic one, if you try to build like matrix operations, then you don't really know how to scale that. There's a very nice framework from IBM, it's called SystemNL, which is open source, which we didn't know, otherwise we would have used, but actually this is a very nice framework for building your linear algebra in a distributed way. And then you need to be careful if you do Scala Spark, if you like functional programming. If you have never done, then I strongly encourage you to do so. There's a little bit of inconsistencies. So what is a fold in Scala is not such thing in Spark. What is a collect in Scala is not the same as in Spark. Same if you do map values in Spark. In Scala, you do map values on a dictionary, on a hash map. So if you do in Scala hash map, you do map values, then you preserve the uniqueness of the key. If you do that in Spark, you don't. So the good thing was that both Spark and Scala were very good tools for prototyping. And we even use the same production stack we use in production. We use notebooks for exploratory analysis, but then we move the code back into the framework as soon as possible. And that means that at the end of the hackathon, we had an MVP. Now, just to recap quickly, what I told you at the beginning of the talk, that we got inspired and we got guided by principles in the manifesto of professional data science. We tried to follow almost the most we could. So, for instance, we tried to remove any manual intervention by uploading everything in a single file execution. Then we, of course, focus on solving a problem rather than regardless of the model, but you have the problem, then use the model to solve the problem, not the other way around. A few things, for example, the validation of data, the hypothesis testing, this was not very well automated because we had to do that as a pre-processing, so we do manually before the hackathon. We built, that was very important, so as I told you at the beginning, very important, before you start building any model, you want to first have an evaluation framework that with metrics that match the quality of your final application. And then, so this one, we really skip that one because we want to do Kaggle-like, and Kaggle only wants one single metric. But in general, imagine you're in an enterprise environment, you don't really want to evaluate your models with a single number. It makes no sense at all. Imagine you're a binary classifier, you take the area under the rock, makes no sense. So you have to think carefully of the meaning of the metrics you use, and generally one metric is never enough. So, and also this one was very important because we started from scratch. With no idea, we had to brainstorm locally, on the spot. So how do you do open-ended research? But at the same time, you also want to, it's a constraint. You have open-ended research, but you also want to deliver something in a deadline. We do that because it's just an excuse. In the research, you can break down research in very small tasks. So your big research problem becomes a bunch of small research little problems that you can time box them. And time box in the sense that I'm going to go free, I'm going to do exploratory analysis, I'm going to try out stuff, I'm going to read stuff, I'm going to do whatever I want to do in this time frame. And then at the end of the time frame, I'm going to do that, I'm going to draw a line, I'm going to say, okay, all the findings, all the knowledge I have acquired so far, now I'm going to turn that into code requirements, working code requirements. And that's it. So we almost finished the talk. Just before to leave, I just want to remind you that if you really want to do innovation, it's not just a matter of technology. So the reason why we were so successful in 5 days, everything that I showed you, we built in 5 days. And that was just because of the technology. It was great because we had an environment where we could set some goals that were free of distractions, 24 hours a day, no distraction, no emails. There was no connectivity, zero. No one could call us. There was no one really interacting us. We didn't have to care about anything about our company. We could come back to London and, maybe Barclays was on fire. We wouldn't have realized. Then the next thing is that you have even more pressure on you. But not because your boss is telling you, oh, you're going to do that. You need to give me that by the end of the week. No, no one told us. We were so much motivated because the motivation came from the group. Because we set the goals and we're going to do it. No one was present. And the best thing ever about offsite in general is that, or hackathon, is that you can fail safely. You try something, you go to sleep, it didn't work, you wake up next day, then try it. That's good. That's how you make innovation. This is just some readings. If you're interested, you can find the original article on the Cloudera engineering blog. So back in time, we were a customer of Cloudera, so we published this use case on their blog. You can find the link of the manifesto. The code of the whole recommender is available on GitHub. And because last time I got a few questions about Spark, things like, oh, should you use the Python API or Scala API, or how you do Agile in a data science context, and so on. If you really are interested on Agile, Spark, generally data science in a more engineering way, then I recommend you read this blog. It's my blog. I publish all the stuff there, so you can find it interesting. Thank you very much. I give you just less than 5 minutes because we rushing the schedule, I guess. Or I don't know. We have 1 hour and 15 minutes, so we have time for a couple of questions, and then we go to the next talk. If any questions, of course.
So Gianmario, great talk. Okay, very, very good talk. So I have a comment on your last slide. When you say fail safely, I would also say fail cheap. That's what we are trying to do in my company, right? Failure is allowed as long as it's cheap. It doesn't cost much for the company. But that's company. Then I have a couple of questions. I'm sort of down in this field, but you say that you can sort of forget about the tail. The tails. How true that is. Because in my opinion, tails are very important, and they basically screwed up all your assumptions. Okay? And then the second question is, based on my understanding, you found a lot of limitation in the linear algebra packages available, right? That's what I found myself when I tried to implement a recommender on a big amount of file. And at the end of the day, it was much easier to implement a gradient descent myself. Few lines of code in Rust smoothly, very good result. So I'd like to get your feedback on these two factors.
Right, so around the phase, if we want to do the video here, there's a difference between when you do like hackathon or like innovation lab, whatever, where all you're doing is brainstorming and hacking, right? So in that case, you really want to prototype, and you want to build a proof of concept really. In a production environment, you don't do that. Right? So it's very two different things. So when I say fake, I mean like implement something, then run evaluation. Evaluation says, oh, your precision is 1%. That's crap. That's what I mean by fake. But by doing this iterations, then each single time you learn some knowledge, and you go and improve it. Important is that your product is always, if you have a baseline, that's why I say always build a baseline. Because you want to be one of the first principles of Agile. Any point in time you stop working on a project, you get something working. So it's very important to always have something working. And then in your spare time, you can try whatever you want. Here, I'm more meaning that if you're in an offsite, then no one is judging you, like just your group. So that's what I mean by feeling safe. The second question about linear algebra, yes, you need to find a trade-off. I generally tend to be faster on implementing things my own. Now, in particular case, the linear algebra through broadcast variables, by implementing our own processing